This is something that I wanted to mention, that similar lectures I have given and some resources are available on the internet. So I gave a set of lectures, 6 or 7 lectures in this StatsFit school, which is available at this. So this is not live recording, but there are PDFs available for so things that I'm showing on the screen. Not all of that stuff, but some of that stuff is actually in this PDF. So later on, you can look them up if you want to study this further. So, right. So in the morning today, I was talking about this Landau theory of phase transitions, where one writes down this starting point is this free energy functional. This free energy is a functional of the order parameter field. And I told you about mean field theory, where one says that this order parameter field has the same value everywhere in space. And then there is only one parameter, which is this average value. And then one can minimize the free energy with respect to this parameter to find out what value it should have. And this is something that we had done, that if there is a characteristic temperature at which this new minima develop. So at high temperatures, one is here, T bigger than Tc, the minimum is at phi average equal to 0. That's a disordered phase. And as you go to a temperature at which this coefficient changes sign, then one sees this other minima developing. And that is basically the description where the order parameter is going from 0 to some non-zero value. And that is basically the description of the phase transition in this mean field theory, where one ignores the fact that actually the order parameter field will be different in different points in space. One assumes that it's the same at every point in space, and then does this approximate theory. Doing that, one gets these critical exponents that I told you about. So this shows that in mean field theory, MFT is mean field theory, you get these values of the critical exponents alpha, beta, gamma, delta. Unfortunately, it turns out that in 2-dimension or in 3-dimension, the actual exponents that one gets are quite different from what one is getting from mean field theory. So 2D Ising model, the exact solution says that there's a big difference between what one gets here and what one gets there. 3D, there is no exact solution, but there are good numerical studies from which one can get the values of the critical exponents. And again, the values are quite different from what one gets in mean field theory. So the basic assumption of mean field theory that one can ignore spatial fluctuations of the order parameter field doesn't seem to be working. It doesn't give you the right result. And so one has to have more sophisticated theory to take into account these fluctuations. But it's a difficult problem because critical point is some kind of a very peculiar point. At this point, we just have found that correlation length diverges. Fluctuations become very, very strong. So there, it's not so easy to take into account these strong fluctuations, long-range fluctuations in a theoretical framework. And I think I had said a few things about that in the last lecture, that how to deal with this theoretically. That framework was developed by Ken Wilson, which is known as the renormalization group framework. Of course, I mean, it's a quite advanced topic, so I mean, I really don't want to go into the details of the renormalization group calculations, but I thought it would be useful for general audience, I mean, people like you, to sort of have some idea about what are the basic ideas that go into that kind of a description. And so I'll spend some time in the last lecture today to give you a physical picture, so to speak, of what renormalization group actually means and what one is doing when one is actually doing a renormalization group calculation. So, okay. So before going into that, let me just mention that I had told you about 2 different kinds of phase transition: first order, continuous, etc. So far, I've been talking about continuous phase transitions, for which you have this critical phenomena, fluctuations becoming very, very strong, and so on and so forth. But of course, I mean, many phase transitions are also first order, and one can this picture is just to show that one can also describe first order phase transitions using the same kind of Landau theory, except the form of the functional is going to be different from what we had done earlier. So when we were talking about the Ising model, we said that only even powers of this order parameter comes into the free energy functional, because S going to minus S, these two are equivalent. Ising model, positive magnetization and negative magnetization, these two are equivalent in the sense that the Hamiltonian has this up-down symmetry. But there could be many situations where this is not so, that up-down symmetry is not there. And there one could have odd powers. So earlier, just to remind you what we did, earlier the free energy was a function of the order parameter, square and fourth power, only even powers. But now we are saying that this up-down symmetry is no longer there, so odd powers are allowed. And then the simplest odd power that you can have is you put in a S cubed term. And then you look at this as a function of S. And the behavior becomes quite different. Because of this S cubed term, a new minimum develops. And there is a characteristic temperature at which the free energy at the origin, which is the disordered state, when S is equal to 0, that's the disordered state. And the free energy there, new minimum, they become the same. And so then, and as you go to still lower temperatures, this minimum becomes lower. So as a result, there is a transition from the disordered state to ordered state with non-zero value of S. But this transition involves basically discontinuity. One is going from 0 to some finite value. And that is basically what one means by a first order transition. So Landau theory can also discuss or describe first order transitions with appropriate form. And of course, form of the Landau theory as a function of the order parameter, that will depend very much on which problem you want to solve. And depending on the symmetry, etc., one can have what I was talking about earlier, only even powers of S coming into the picture, or even and odd powers coming into the picture, and depending on that, you could have either a continuous transition or a first order transition. So, but this is all mean field theory. Mean field theory is assuming that the order parameter field doesn't vary in space. So you can have only one number here as the order parameter. And as I said, this doesn't work for phase transitions that we know in 2 and 3 dimensions. So the question is what to do next. There are many things that one can do, but I want to spend about half an hour on this framework, which is called renormalization group theory, to try to give you some idea about how one can treat this effect of strong fluctuations near the critical point by doing what is known as a scaling theory. And the scaling theory, I have already told you about some scaling functions and this and that. The name scaling comes from the fact that in this kind of theory, what one is trying to understand is how the parameters of the problem change when you change the scale of the theory. Let's say we start with lattice model, where you have a lattice given by this lattice sites given by these little circles, and you have spins or variables at each of these lattice sites. That was the original scale, and there the length scale is set by the lattice spacing. Now, what one can do is this. What is known as coarse graining. Instead of looking at the smallest length scale, lattice spacing, I will do this block. The lattice is divided into b to the d, or in this case, b squared to 2 dimensions. Lattice is divided into blocks. And these blocks I have tried to indicate by these dashed lines. And these blocks are identical. That lattice, of course, extends over this way or that way. So the whole lattice is now divided into blocks. Each block is a 3 by 3 block, or b by b block. B is equal to 3 here. So each block will contain then 9 lattice sites. So there are variables, original variables defined in the lattice sites, and there the length scale is 1, let's say, 1 in units of lattice spacing. And then from that, I am trying to go to a coarse-grained picture in which the lattice is divided into blocks, and the length scale of this block is b, and b is equal to 3 here. So each of these blocks will now contain b to the d, b raised to the power d sites. At each site, you have a spin variable sitting there. And here, b is equal to 3 and d is equal to 2, so you have 9 site variables sitting in every block variable. And then what one does is one tries to describe the system in terms of block variables. Earlier, system was being described in terms of the site variables, which are sitting at individual lattice sites. Now we can define, again, a spin variable for each of these blocks. And each of these blocks will now have, let's say I call it a block spin. A block spin will then correspond to 9 site spins. And one defines a transformation from the site system to the block system, saying that the block spin reflects the collective behavior of the site spins which are inside the block. So here we have 9 site spins, and then one can define some kind of a total value. I mean, each of these can be, let's say, for the Ising model, each of these site spins can be +1 or -1. So we have 9 of them. And the sum of all these +1s and -1s that are inside a particular block, that could be positive or negative, right? If 4 of them are up and 5 of them are down, then you have a -1. If other way around, 6 of them are up and 3 of them are down, then you will have +3, etc., etc. So one can define a sign of the sum of all the spins which are sitting inside a block. And this sign itself will have +1 and -1 values. So the sign I can call another Ising variable. So this block variable reflects what is going on inside the block itself. The block variable reflects the collective properties of the site spins which are inside a particular block. And this is what is known as coarse graining, and this is one of the standard procedures that one uses in statistical mechanics to go from one length scale to another. So what one is doing is one is going from the original length scale, which is 1, to a length scale which is b, or in this case b equals 3, and one is defining new variables for each block which has the same symmetry as the original site variables, but this new block variables will now reflect the collective behavior of the site spins inside a particular block. Okay? And then you can try to describe the whole system in terms of these block variables. So you have already seen, so why do we want to do that? The one simple reason is that the number of block variables is smaller than the number of site variables, because each block contains some b to the d site variables. So you have already, if you can describe the system in terms of the block variables, then you have already reduced number of degrees of freedom. Originally, we had spins sitting at individual sites, but now you have spins sitting at these sites, centers of the blocks, and the number of such block spins is smaller than the number of site spins by the factor of b raised to the power d. In this case, b is 3 and d is equal to 2, so the number of block spins is smaller by a factor of 9. And you have reduced the degrees of freedom, number of degrees of freedom. And if you, then you have a new Ising model where the spins are sitting on these blocks, and there is nothing that says that you cannot do it again. You can do it over and over again. So at each application of this blocking transformation, you are reducing the number of degrees of freedom by an amount which is this scale factor b raised to the power dimension. And if you want to apply these transformations one after another and so on, that way every time you are going to a system with a smaller number of variables, which is of course easier to handle. And these transformations going from the site variables to the block variables by doing this coarse graining is basically what is called a renormalization group transformation. And this construction that was first proposed by Kadanoff, so carries his name, but this is the basic idea. Now, how to implement this idea, that requires many technical things that we'll come to we'll not have time to discuss, but a few things that follow from this kind of a construction is what I want to point out in the next half an hour or so. So do you get the basic idea that you start with spins sitting at lattice sites, and then you define blocks. Each block contains certain number of lattice sites, and each block will now have one block spin. And one wants to, originally the model was defined on the site variables, and it had some parameters. So as you go from the site variables to the block variables, you will have new parameters. So the question is, if I now want to go from a description in terms of the site spins to a description in terms of block spins, then how the parameters for the block spins, how they will depend on the parameters that you had for the site variable. And if you can solve the problem, then you can apply this transformation iteratively. Each time you're reducing the number of degrees of freedom, and eventually you will be able to solve the problem. That's the whole story. Technical aspect is how the transformation from the site variables to the log variables, and transformation now will be in terms of the parameters. So if we have an Ising model, the site variable had parameters like the coupling constant and the magnetic field. And so these block variables, again, will have similar parameters, how one block variable interacts with another block variable. That will give you a coupling constant. If there is a magnetic field, again, in the block description also, there will be a magnetic field. But these two things, coupling constant, magnetic fields, they will not be the same as what you had for the original site variable. So what you have to do is you have to find out how the new coupling constants depend on the original coupling constants that you had in the original model. And if one can do that, then that, in some sense, is a way in which you can try to solve this problem. There is some loss of information. I mean, you cannot, you see, once you have defined the block spins, from there you cannot go back to the site spins. So some degrees of freedom you are summing over. But eventually you see it is in some sense not loss of information, it is doing the problem in parts. Like, in statistical physics, let's say if you want to do it from first principles, you would write down the partition function. Partition function, you have to have a sum over all the spin variables. What this is doing is, instead of doing that sum for all of them, one is doing it in steps. So first of all, doing this coarse graining, you have done sum of the sum. The sum over the spins which are inside a particular block, that sum you have done. But still, there are still many variables which are left with the block variables. So subsequently, you have to do that sum. But that sum also will do it by doing another block, by applying this over and over again, this transformation over and over again. So instead of trying to solve the whole problem in one go, that summing over all the spins, what one is doing is summing over a fraction of the spins at each application of this transformation. I'm sorry? At this level, it is. Because if we had some disorder in the system, that the coupling here and the coupling there are different, then you will have to deal with a whole lot of coupling constants, not just one or two coupling constants. So here, when I define the Ising model, I don't assume that this interaction parameter is different for different pairs. I assume that they are all the same. So that reduces the number of parameters. But if the system is inhomogeneous, if you have different J's at different parts of the system, then you have to deal with this whole set of J's that are there in different parts of the system. So in principle, one can still do that. I mean, this blocking, it doesn't say that it has to be done for a homogeneous system. But if it's inhomogeneous, then you have to deal with a very, very huge number of parameters, which in practice you cannot do very well. Okay, so now if you get this basic idea that one is trying to do a transformation that takes you from the site variables to the block variables, and then one is trying to find out how the parameters that specify the system, the interaction parameters, magnetic field, etc., how they change under this transformation, then from that one can actually derive the scaling picture that I had tried to tell you earlier, which people had done phenomenologically, that the free energy is a function of some combinations of the temperature and the magnetic field. So I think I'll be able to go up to that point at least. So this is basically saying what I have just told you about. The lattice spacing of the block spin is B times the lattice spacing of the side spin problem. So each block is B by B. So the lattice spacing of the block spins also form a square lattice. So I mean, if I look at this picture, these spins themselves, they form a square lattice. But the lattice spacing is now 1, 2, 3 times the spacing of the original lattice. So this is something that is obvious. So if I have a correlation length measured in units of lattice spacing, then, well, it's not written here, but it will come to in a minute. So there are two things that I consider here. One is the correlation length of the system. The other is free energy per spin. Okay, and we try to find out how the free energy and the correlation length change as one goes from the side spin system to the block spin system. Okay, so this transformation from the side spin to the block spin system must leave the total free energy unchanged. That's why a requirement that, since the total free energy is something that describes the physical properties of the system, that should not change as one is going from the side system to the block system. Total free energy is number of spins multiplied by free energy per spin. So for the side spin system, you have number of sides, ns, and this F is the free energy per spin. For the block spin system, number of spins has become number of blocks, and again, the free energy, but these parameters will change. That's what I'm saying. That as one goes from the side spin to the block spin, the parameters in this problem, parameters are temperature and magnetic field. These two parameters will not be the same as that for the side spin system. They will be functions of the parameters of the side spin system, but in general, they will be different. So the parameters which then specify the block spin system, that I call T with a tilde and H with a tilde. So if T tilde and H tilde, this is the free energy per site for the block system. And there are NB such block spins. And so this is an identity which says that the free energy per spin remains invariant. Free energy per spin for the side spin system multiplied by the number of sites, and free energy per spin for the block spin system multiplied by the number of block spins, these products have to be the same. And so that relates this with that. And I have also defined the correlation length of the system, and this correlation length plays a very important role. It becomes infinity at the critical point, which is a very important property of a critical point. So the correlation length for the block system will be measured in units of lattice spacing of the block system. And so there is this relationship that the correlation length measured in units of the lattice spacing for the block system and the side system are related by simply 1 over b. Length is changing by factor of b as he was going from side system to the block system. So these two are relationships that relate the free energy of the side system with the free energy of the block system, and the correlation length of the side system with the correlation length of the block system. This is nothing but, this is just obvious in the sense that one is keeping the free energy invariant, and length, if you use different units to measure it, as you change the unit, the value of the length itself will change. So let's see what does this take us. So basically, you know that number. What happened? I'm going in the opposite direction. Okay. You know that number of side spins and the number of block spins related to each other by this factor b to the d. Each block has b to the d sides. So number of sides divided by the number of centers of the blocks is given by b to the d. And that tells you about how the free energy per spin scales or changes as one goes from the side spin system to the block spin system. Yeah. And also, now one makes use of the fact that you have this correlation length which diverges at the critical point. So the critical point for the magnetic system is when little t is equal to 0, temperature is equal to the critical temperature, and there is no magnetic field, where this correlation length goes to infinity. But if you divide infinity by b, then it's still infinity, right? So the correlation function, when the correlation function for the side spin system goes to infinity, the correlation function for the block spin system also has to go to infinity, because these two are related to by this factor of b. So it just says that at the critical point where this xi goes to infinity, then xi for the block spin system must also go to infinity, which in turn means that critical point basically happens when this t and h are equal to 0. This t tilde and h tilde should also be equal to 0. This again, I'm not doing any sort of fancy mathematics or anything like that. This is just, and that's the whole idea of renormalization group, is try to find out how the description changes as you go from one scale to another. That's why it is called scaling theory. So the whole idea is that we are going from a scale of individual lattice parameter, lattice distance, to a scale which is b times bigger than that. And then we are trying to see how the description of the system change when one does this scale transformation. And just at the critical point where the correlation length diverges, that means that correlation length from the side problem diverges, correlation length from the for the block problem also diverges. So the critical point in the side problem, which is little t equal to 0, h equal to 0, must also give you this t tilde, h tilde equal to 0. And this is called a fixed point, that now there is a transformation that takes you from the site to the block. And this transformation tells you that this t tilde and h tilde, these are functions of t and h. And these functions must be such that when I put t equals 0 and h equal to 0, then I get back t tilde equal to 0 and h tilde equal to 0, which in turn means that critical point corresponds to what is called a fixed point of the transformation. And this is something, the fixed point concept is something that I'm sure all of you are familiar with. I mean, when you do dynamical systems and things like that, then there are special points such that those are transformed to itself. Functions as such that if you input those points, then you get back the same. So here is the same thing. The critical point here is a fixed point because at that point, correlation length diverges. Correlation length diverges. If it diverges for the side spin system, it must also diverge from the block spin system. And so a critical point for the side spin system must then map onto the critical point of the block spin system. And if the only two parameters are there, one is the temperature-like parameter and one is the magnetic field-like parameter. Critical point for the original problem where both of them are set equal to 0. And this mapping then tells us that this t tilde and h tilde also will be 0 for these values of t and h. So critical point is scale invariant, so this is a fixed point of a scale transformation. This is something that this is the heart of the RG theory, that one is dealing with a system which becomes scale invariant at the critical point because the correlation length diverges. There is no characteristic length scale in the problem anymore. And if you have such a system, then system must remain invariant under a scale transformation because infinity goes to infinity, even if you divide it by a factor of b. So, and that corresponds to a fixed point of this renormalization group or the scaling transformation. So this is the important thing. First of all, there is this notion that you can describe the system at different length scales. I mean, original model was for a length scale which corresponds to individual lattice spacings, but now we are getting a problem where the length scale is b times the individual lattice spacing. And we are trying to describe that system now with new parameters, which are functions of the old parameters. But if the problem has a second order phase transition, then that critical point, the parameter values corresponding to that critical point must be a fixed point of the transformation that takes you from the side variables to the block variables. Right? So let's see then, till now it is all argument. I mean, there is no calculation has been done. One is just saying that I do this transformation, I go from the side variables to the block variables, try to describe the system in terms of the block variables, and we'll need new parameters, t tilde and h tilde then. I have not told you anything about how these parameters are to be calculated in terms of the old parameters. That is the machinery. But one can make arguments without actually going into that actual calculation. because these are general arguments that there should be correlational length must change by a factor of b. So if it is infinite in the side version, must also be infinite in the block version, and so the critical point, which is scale invariant, the parameters should not change as one goes from the side to the block. One can do more even without doing any actual calculation. So we have found out that if t and h equal to 0, then t tilde and h tilde, they also should be equal to 0. So now we look at small values of t and h, close to the critical point, not at the critical point, but close to the critical point. Then the simplest way that this t tilde and h tilde related to t and h are by simple proportionality. Because I know that t tilde is equal to 0 when t is equal to 0. I know that h tilde is equal to 0 when h is equal to 0. So there are, of course, many functional forms that one can take. But the simplest one is this, that they are simply proportional to each other. And the proportionality factor should involve the scale factor b, by which you are changing the lattice spacing. At this point, I don't know what this f1 and how these functions f1 and f2 look like. But again, one can argue, one can use sort of very general arguments to guess how these functions will depend on b. And this is that argument, that if b is equal to 1, then I have not done anything. B is the block size. So the original problem, spins were at individual sites, but if I don't do any blocking at all, that corresponds to b equals 1. It just block spins are the same thing as the side spins. There is no distinction between these parameters and that parameters. So whatever functional form we have here, that must go to 0, not go to 0, go to 1 when we put b equals 1. That's again a triviality. That b equals 1 is means that I have not done anything, so there is no change in the parameters. If I now have two such transformations, first one with b2 and the second one with b1, then that is equivalent to a single transformation by a factor b1, b2. That's what I'm doing. I'm changing the lattice parameter by a factor of b. So I first change it by a factor of b1, and then change it again by a factor of b2. That basically means that the whole thing has changed from the original lattice by a factor b1 times b2. So these functions, they also must satisfy this relationship. That if I have b1, b2 is the same thing as individual transformations, first one with b1, second one with b2. Doesn't matter which order actually. This is basically, you can do first b1 and then b2, or first b2, then b1. The whole effect is the same thing as doing one transformation with a factor b1 times b2. Now you can easily convince yourself that these conditions are satisfied if I assume that these functions are these power law forms. As you can see here, if b raised to the power some exponent, I don't know what this exponent is. Similarly, I don't know what this exponent is, but it has the property that when b is equal to 1, then this is equal to 1. And if I do this, obviously, if I take b raised to the power b1 times lambda 1 and b2 times lambda, then it's same thing as b1, b2 times raised to the power lambda. So this is then, we assume that these functions, f1 and f2, which tell us about how these parameters change when they're slightly different from 0, is a proportionality, and these proportionality factors are simple power laws. And this power law will satisfy the group properties that these transformations have. Here? So here I'm just saying that this function, if it is some power of b, then these conditions are satisfied. But I don't know what power. So the first power, when f1 corresponds to the temperature, so that I call lambda sub t, and the second parameter f2 that comes from the magnetic field, so I call lambda sub h.
They're just parameters, two different parameters.
Yeah, at that point, I don't know. Since I have not done any calculation, I don't know what these parameters are. But these are things that you can guess, that you can derive by just logical arguments. That if you understand what one is doing in the scaling transformation, then general properties of the scale transformation, one can come up to this point. But this, till now, I don't know what this lambda t is and what this lambda h is. But now you see that from this, one can derive this scaling form for the free energy. So there are these two things. No? We told you that the free energy has to be related to the free energy of the block spin system by this factor b to the minus d. Now I know how to relate this t tilde and h tilde to t and h. So I just go back and do the same, put that in. The singular part of the free energy is a function of reduced temperature magnetic field. So this is b to the minus d, and then singular, same thing calculated for t tilde and h tilde, but I know that t tilde is basically b to the lambda t multiplied by t. H tilde is again similarly that, but some other exponent. So this basically then follows from the basic properties of this transformation that I have just told you about. It must keep the free energy invariant. That's where this b to the minus d come in. The t and h will change, but t equal to 0, h equal to 0 is a fixed point, and very close to that fixed point, one can assume some kind of a proportionality, and then making use of the properties of this transformation, I can I get that this proportionality, these functions must be power law functions. But this lambda h and lambda t, I don't know, and what is the form of this F singular, that itself also I don't know. Right? And this should be true for any value of b. So if I want to further simplify things, I will choose b such that b to the lambda t multiplied by this reduced temperature is equal to 1. Then I can eliminate the factor of b by using this, write everything in terms of t and h, and then one gets this formula, that singular part of the free energy is some power of reduced temperature, and then there is a scaling function of h divided by, again, some power of t. Right? So going from here to there is just simple algebra. But what is nice about this is something that I had told you several transparencies ago. I don't know whether I can go back to that easily, but here. I told you that this is when I told you about this, this was basically the level of phenomenology. That just by looking at the behavior of the critical exponents, people sort of assumed that this formula is valid because this formula will give you the correct relationships among the exponents. So now, in some sense, one is deriving this by this scaling argument, that if I go from the original scale to a scale which is b times that, try to describe the block spin system in parameters of the block spin system in terms of the parameters of the side spin system, make use of the fact that the free energy doesn't change. That's two facts. Free energy doesn't change and the correlation length diverges at the critical point. Just making use of this, then one obtains the relationship that I just got to. This relationship. And the one that I just showed you, there you had 2 minus alpha here, and you had beta plus gamma here. So those critical exponents now are then related to these two exponents, lambda t and lambda h. So if I have a calculation where I can calculate the h tilde and t tilde from h and t, from that I will have a calculation of this lambda t and lambda h. And if I have that calculation, then I can relate these values to the exponent values alpha, beta, gamma, etc., etc. So that's basically the idea. And of course, I mean, one eventually has to implement that idea, and that is where the difficulty comes in. A few other things also one can derive without actually doing the full calculation. So as I said, the scaling form that we get is identical to the phenomenological scaling form with this identification. D by lambda t has to be equal to 2 minus alpha, and lambda h over lambda t should be equal to beta plus gamma. So if there is a calculation of this lambda t and lambda h, then from that one can calculate what the critical exponents are going to be. There is another thing that one can guess. As I said, the correlation length for the block system and the correlation length for the side system are related by 1 over b, because one is changing the scale of length by a factor of b, and one is looking at a length. So the length basically changes by a factor of 1 over b. And if we say that the correlation length has this behavior, this defines the exponent nu, then one can relate the lambda t to the exponent nu. And this leads to a relationship which is known as hyperscaling, which is also satisfied by the scaling exponents that one has in 3-dimensional, 2-dimensional systems. So this is, I guess, time is more or less up, right? 5 minutes, yeah. So this is the outline of what renormalization group theory is all about. I think it is better, instead of calling it renormalization group, one should call it a scaling theory, because this theory is about how the parameters which describe your system, that describe the Ginzburg-Landau theory, the free energy functional, how these parameters change as you go from one length scale to another. And one is going from the lattice spacing length scale to the block spacing length scale by doing some kind of a coarse graining. And the actual calculation then will tell you about how the parameters of the coarse-grained problem are related to the parameters of the original problem. And if one can do the calculation, then doing the analysis that I just told you about, that you find the fixed point, and then you find out near the fixed point how the variables change. From that, you can find out what the critical exponents are going to be. And the procedure that implements this, that depends very much on that depends very much on what kind of system you're dealing with. One can do this procedure in real space. One can do this procedure in Fourier transform space. That's what most people do. And there are lots of technical things that one has to worry about. But this procedure has been successful in predicting the correct values of the critical exponent, which mean field theory cannot do. That I've just shown you that the mean field theory predictions for the critical exponents are not the same as what you actually have. So that correction, that fact that if you take into account fluctuations, that in principle is accomplished by this framework. So just maybe the last transformation. So this is basically what I told you about renormalization group. What one means is repeated application of this scale transformation. One goes from a lattice problem to scale transformation by blocking, and then from the lattice variables, the variables of the lattice scale to the variables of the block scale. And if one can actually do this mathematically and do the calculation, which is not a trivial thing to do, but people have developed methods for doing this calculation, then you know the parameters of the block Hamiltonian in terms of the parameters of the site Hamiltonian. And then you do these things that I just told you about. Look for a fixed point, and then you look at small deviations from the fixed point and how the block variables depend on the site variables. And from that, one can get information about the critical behavior of the system. So not just here we're talking about still equilibrium problems, but whenever you have a situation where you have a critical point, that there is a length scale that is diverging, then this kind of a procedure is very useful, in the sense that in principle, then you can calculate the behavior near that point where the length scale is diverging. And there are many other things that you can calculate, but again, Since there is not much time, I'll stop here. Take some questions if there are any for the 4 lectures that I have given. And I gave you the.
Can you give them the? Give them your email.
Yeah. It's. All lowercase. cdgupta@iisc.ac.in.
And really covered.
So there are many things that I had to sort of gloss over some things, but if you are interested, you can look up those notes that are there at that website, and this will sort of fill in the blanks in some cases, the details that I didn't have time to get into.
Equalities, but not the inequalities. Yeah.
But generally, I mean, equality is found here.
Inequalities are no.